Okay, good morning. We continue the lesson with limits of functions, so I skip some pages for the time being. So this will also be included in the coming exam, okay? So limits of functions, actually the concept of limits is actually a very important concept in mathematics. Even though probably Newton was the first guy who was thinking in that way, but it was not until the beginning of 20th century we didn't have a very rigorous definition of the limit of functions. So this is what I'm just trying to say, is that the concept of limit is a little bit hard. Yes, if you want to understand it in a very good way. I will try to do my best to transfer the ideas to you. But what you need to know is how to calculate limits rather than focusing on the real concept of limits. Because even if you go to university, if you want to be a math major, then probably you will delve into this concept a little bit more. But we need this for the next chapter that we are supposed to talk about derivatives. Okay, so what do I mean by limit of a function? So let me give you a concrete example. So consider this function, which is also given in your book. So f of x equals to x squared minus 1 divided by x minus 1. If I ask you to calculate the value of f at 1, then hopefully you agree with me that this is undefined. Because if I replace x with 1, the denominator becomes 0, and division by 0 is forbidden. So it's not defined. But except 0, I can actually plug in any other values for x. So it means that I can try to understand the behavior of the function at numbers very close to 1, but not equal to 1. So these words that I'm emphasizing are the core words, or terminologies you need to understand it. So for example, let us understand the behavior of this function when x becomes close to 1, because you know that you are not allowed to choose x equals to 1. Let us understand the behavior of this function when x is close to number 1. Of course, the notion of closeness and being far is actually a relative concept, yes? So what do I mean by close? Okay, let us try to understand this a little bit. So x equals to 1, let us concentrate only on one axis here. Here is 0, here is 1. Okay, close to 1 means the numbers around 1. But when I say numbers around 1, it might happen that the numbers are close to 1 but greater than 1. Or it is possible to have numbers close to 1 but smaller than 1. We have to treat these two situations differently. Okay, so let us focus for the time being on numbers close to 1, but all of them above 1. But one point is this: wherever you start, it doesn't matter for the beginning, but you want to understand the behavior of your function when you are close enough to 1. So what does it mean? It means that if I start from here, I will choose the next number a little bit closer to 1. And I will choose the next number a little bit even closer to 1, and try to see how my function behaves in this process that I am getting closer and closer to 1. But now I am approaching 1. These terminologies I want you to understand. So I'm approaching to 1 from the right-hand side, from the numbers above 1. So let us set up a table, okay? For example, let us not go very far away from 1. So let me choose x to be 2. Okay, and then I put 2 here. We can calculate this in our head. It is not hard. So I put 2 here. 4 minus 1, 3. 2 minus 1, 1. 3 divided by 1 is 3. Yes, so if I am at 2, for example, assume that this number is 2 here. When I choose 2, the value of the function becomes 3. Let me go a little bit closer. For example, let me choose 1.5. If you take your calculator and put this number here, make sure, I want you to understand there is no problem with 1.5 here. Because if I put 1.5 here, it becomes 0.5 in the denominator, which is completely acceptable. If I put 1.5 there, if you raise it to power 2, it becomes 2.25 minus 1 is 25, and then you can calculate and find the answer. So the answer will be 2.5. Yes? And now, let us go closer to 1. For example, let me make it 1 point, for example, 2. You see, so what I am doing, I have started from a point which is above 1, and I am trying to get closer and closer to 1 to see what happens for the values of my function. Okay? That's what I'm doing here. And to see if there is something that I can understand here in the behavior of my function. Okay, so if I put 1.2 there, so what happens, you will see that the answer becomes 2.2. It's not hard, by the way. And if you go a little bit closer, so let us take 1.1, and if I put it there into this function and calculate everything, so the answer becomes a 2.1. And then if I put this even closer, you see what I'm doing. I have started from a point above 1, and I'm approaching, I am getting closer to value 1 from above, okay, from the numbers greater than 1. And then I am seeing what is happening to the values of my function. So what's happening then here, this becomes 2.01. Yes, so if you don't mind, let me just go a little bit more. So if I take another number 1.001, so what is happening now, if you calculate this, it becomes 2.001. Yes, so it is completely understandable. The behavior of the function is understandable based on this table. So what is your intuition? I'm asking for your intuition. Of course, there is no place for intuition that much in rigorous mathematics. Intuition will help you to discover something, and then at the end of the day, you have to make it very rigorous. But making it rigorous at this level is impossible, more or less. Okay, but I want you to understand what is going on. So can you see what is going on? First of all, let me just repeat. I was not able to choose 1 for x. Yes? And then I want to understand the behavior of this function very close to x equals to 1. So the natural starting point is what? Is to try to understand the values of the function when x is relatively close to 1. Relatively close to 1 means two things. Here is 1. I can be relatively close to 1, but a little bit larger. I can be relatively close to 1, but a little bit smaller. Now I am investigating being close to 1 from numbers above 1. Yes, so this is what you see. I have started putting numbers which are close to 1. Might be the first number comes to mind is 2. Then I will actually start shrinking the distance of my number to value 1 by doing this. So you see the values are getting closer and closer to value 1. One thing is clear, I am not able to talk about the value exactly at 1, but nothing prevents me to talk about the value of the function at values close to 1. Yes, this is something. And then I started putting these numbers into this function using your calculator or whatever. You calculate these values. So what is happening to the values of the function? Do you see what is happening? Yes? It's approaching 2. Yeah, so it means that the values are getting smaller and smaller in this case, and they are getting closer and closer to 2. This behavior, if you want to write it in a symbolized form, you write the limit of the function f of x when x approaches 1. From the right hand side, you put a plus on top. It doesn't mean plus 1. It shows in which direction I am getting closer to 1. In this table, I have decided to get close to 1 from the right-hand side. So this plus that I put on top means that I am approaching to 1 from the numbers above 1. Is that clear? Is equal to 2. Instead of writing so many things, you can imagine we symbolize this behavior in this symbol. So when you see this symbol, you understand what does it mean. It means that the values of the function can be close to 2 as I desire, but there is a condition for that. I have to make x close enough to 1. So it is these words. So I can make the distance between the values of the function. Be careful about these words if you are a little bit interested. But of course, you don't need to be worried about these really precise definitions. But that is the definition of limit, actually, in words. So the values of the distance between the values of my function and this number 2 can be made arbitrarily small on the condition that I make x close enough to 1. Is that understandable? So it means that, can I make the distance between f of x and 2 smaller than 1? Yes. For example, it is enough to stand here, and then the value of the function is 2.5. The distance between 2.5 and 2 is 0.5. So I was able to make the distance between the function and its value is smaller than 1. Yes? Can I make the distance between my function and 2 smaller than 0.2? Yes, it is also possible, but not if I am far away. So I have to get closer to 1. If I get closer to 1 at this point, the distance between this value and 2 is 0.1, and the distance is smaller than 0.2. Is that understandable? Can I make my distance to 2 smaller than 0.02? Yes, but I have to go closer. Yes? So this means this behavior that you can get close enough to this value on the condition that you make yourself close, sufficiently close to this number, is symbolized in mathematics by this. Yes, and then be careful, there is no approximation going on. This is important. So when I say the limit of my function, so let me just write it like this. When I say the limit of a function f of x, when x goes to a or approaches to a or tends to a from the right hand side is equal to L, what does it mean? It means that the values of the function become arbitrarily close to this on the condition that the distance between x and a are sufficiently small. Yes, let me just repeat. I can, so the values of f, the difference between these values can be made arbitrarily small on the condition that x becomes sufficiently close to a from the right hand side. Yes, this is the idea of limits. Is that clear? So this, if for you, this is important to understand. When I write something like this, you need to visualize a table like this. Okay, instead of writing so many detailed information, I just write that. So it means that this is the limit. But of course, you might say that let us understand the behavior of the function when I am getting close to 1, but this time let us decide to approach 1 from the values smaller than 1. Let us see what happens, okay? Let me also do this. So I will actually set up another table. I would write x and I would write f of x here. But I decided to go from values smaller than 1 and approach to 1. So let me start with 0. Probably the natural one is, if I put 0 here, the numerator becomes -1, the denominator becomes -1, and then I divide them, it becomes positive. And now my goal is to get closer and closer to 1, but from the left-hand side. So let me increase it to 0.5. Yes? So if I put 0.5 here, square it, subtract 1 from it, 0.5, and subtract 1 from it, so the answer becomes 1.5. Now let us get even closer. For example, let me choose, I don't know, a 0.8. You see, I'm choosing the values that are getting closer and closer to 1 from the left-hand side. So if I calculate this and put it there, so it becomes 1.8. And I get closer. It becomes 1.9. You can calculate these. I get even closer by increasing the number of nines here, for example. Then it becomes 199. These are not something, so you can just put these numbers in the calculator, okay? And then I just increase it, and the answer becomes 999. So what is happening here? It seems that when I approaching to 1 from the left-hand side, the values of the function are also approaching to a particular number. What that number is? Again 2, yes? To write this behavior, I symbolize it like this. I would say the limit of my function when x approaches to 1 from the left-hand side is 2 again. Okay? This is called the left-hand side limit. This is called the right-hand side limit. It is not the case always that the left-hand side limit and the right-hand side limits are equal. But if they are equal, I would say that then, so we have this scenario as well. So if f of x, x goes to a from the left, might be another number m. In this case, they are the same. If L is equal to M, then the common value is the limit is called the limit of f of x when x approaches a. Okay, and then to symbolize this, I use just x goes to a without any directions. This means that x approaches a from the values larger than 1, x approaches a from the values smaller than 1, but when I write x approaches a, it means that x becomes close to a, but I don't know if this is getting close to a from the left or from the right. Okay? Is that clear? It's not that clear, I know, but let me just try to understand, to repeat this. This table is summarized in this symbol. And this table is summarized in this table. So when you see this, mathematicians understand what happens to the values of my function when x becomes closer and closer to 1, when x is smaller than 1. So they understand that the values of the function are getting closer and closer to 2. When you see this symbol, it means that you should understand that the values of the function are getting closer and closer to 2 if x becomes closer and closer to 1 from the values larger than 1. Okay, so these two, and then if this is the case, that these two numbers are the same, then I would say that the limit, in this case, I would say that the limit of my function when x goes to 1 is 2, independent of the side that I am approaching to 1. Am I approaching from left or am I approaching from right? It doesn't matter for this function, because in both cases the answer is 2. So I would say that the limit of f of x when x approaches to 1 is 2. Yes, this is the idea of a limit of a function. Any questions? Yes?
Why do we not just like simplify that?
Yes, I actually, the reason that I was able to calculate it quickly in my mind, because I simplified it first and then put the numbers in. But still, I want you to understand, if you simplify this, that's a good question, by the way, because everyone knows that x minus 1, x plus 1 divided by x minus 1, it becomes x plus 1. But if you write this function is equal to x plus 1, this is the mistake. So these two functions are not equal, even though in the previous lesson, even I was a little bit careless, but every now and then I emphasize that these equalities are valid if and only if we are working in the domain of the variable. So if I write two functions for you, one function, the function that I have written, and another function, x plus 1, these two functions are not equal functions. Yes, because the domain of this function, what is the domain of function g? The domain means the set of all possible values that you can choose for x. So what is the domain of g? Is R, yes? But if I ask you what is the domain of f, it is not R. It is R, but except number 1, yes? So these two functions have different domains. If functions have different domains, they are not equal. Yes, but if x is not 1, then of course the values are the same. So that's the whole point. So this function can be described at any point, but this function cannot be described at a single point 1, but still it doesn't hurt. We can talk about this function when x is very close to 1. So that is the idea. Yes, that is the idea, that even if you cannot talk about the value of a function at a point, but still you might be able to talk about the values of that function at points close to that forbidden value. And that's exactly important for us. You will see why. Okay, so first of all, is that more or less understandable? So for example, you might say that this is always the case. The left limit should be equal to the right limit. To understand this better, let me try to draw some graphs for you. So what if I have this function? So let me just try to draw a graph for you here. For example, this graph. Assume that this is the function f of x equals to y, and then you have this point A here. And then if I calculate, if I go up here and then I go horizontally, hopefully you realize, because this function is f of x and this value is a, this is f of a. Okay, let us try to understand this function. If I say what is the limit of f of x, if you don't mind, let me call this L. Of course, in this case, L is exactly equal to f of a, but let me just write L here. And now let us understand the behavior of my function f of x when x approaches to a from the left-hand side for the time being. I want you to understand this, yes? When x approaches a from the left-hand side, say that I am here. I am close to a. I am close to a, but I am on the left-hand side of a. What is the value of my function? The value of my function is this much, yes? And then when I get closer to a, but it's still on the left-hand side of a, for example, let us go closer here. And then if I ask you what is the value of the function, you draw this vertical line and you say that this length is equal to the value of the function now. But let me go closer. So what is happening here? Now I'm getting closer and the height becomes this. Okay, I cannot draw more. So if I get a little bit closer, so you see the value of the function at that closed point, that point which is closed is here. So intuitively, can you tell me what is happening when I am getting closer and closer to A? The lengths of these blue lines are approaching to a particular number. What that number is? L. Is that understandable? Yes. So then I would say that intuitively, this is L. Now I want you to tell me the other side. What is your opinion about this one now? Let us understand this. So what do you think will happen? I want to understand the behavior of my function when I am approaching a from the right hand side. So let us just take, for example, let us be here. Here. It's relatively close to a. If I ask you what is the value of your function, the value of your function is this much now. Yeah, so something like this. So the value of the function is this one. But let me get closer. I get closer. What happens to this function? The value of the function, it becomes smaller. And I get even closer. The length becomes even smaller. Okay? And then I get even closer. The length becomes even closer. So what is your intuition? Now these green lines are getting smaller and smaller in length, but then what can you say about this? What is the limit of f of x when x goes to a from the right hand side intuitively? L again. So as soon as you see that these values are the same, the conclusion is that the limit of your function when x approaches a is L. I want you to understand when you have this equality doesn't say you anything about the value of the function f at a. Yes? This only tells you the value of the functions, how function behaves when you are close to a, but not, I emphasize, but not a. In this case, what is f of a? What is f of a? L. So that was a coincidence that in this case, limit of f of x is L as well. Yes? But when you see this, it doesn't give you any information regarding the value of the function of x. Let me ask you another question. This is important, by the way. I take the same graph. Every situation is the same, but I carve one point out of my graph. For example, I take this one and exclude it there. Yes? And I exclude it here. Yes? So this is not the same function, even though the difference is really minor. I just carved out one single point from my graph. But this function that now you see is not the old function. It's another function. So if the previous function was called f, I have to call this function, I have to give this function a new name, g. Why is that? Because the domain of the previous function was the whole R, but the domain of this function is, can you tell me, assuming that this will continue forever? Yes? Except this single point. So the domain of this function is the set of all real numbers except a. Because if I ask you what is the value of g at a, you don't know because that's hollow. It's not defined there. So this function is not different, is different from the previous function. But what do you think about the limits? So in the previous case, f of a was L as well. The limit was also L. But in the new case, if I ask you what is g of a, what do you write in front? Undefined, because a is not in the, g of a is not defined. Yes? But now if I ask you what is the limit of g of x when x approaches to a from the left? Again, L, do you understand? Then nothing will change. Because you will keep yourself on the left-hand side of a close to a and try to approach a. You're not allowed to stand on a. You have to be close to a. In this case, I hope that you see still the situation is the same. These blue lines are growing in length and they are getting closer and closer to L. And now can you tell me what will happen if I approach a for this new function from the right-hand side? What happens? L. So because now the left-hand side and the right-hand side limits are equal, by definition, this is the definition, the limit of the function g of x, x approaching a, is again L. Yes? But what is the difference? Here, this is not equal to the value of my function. This is equal to the value of my function. Okay? This is, by the way, it was not that easy for mathematicians to understand that, because every human being has an intuitive idea about continuity. So if I ask you, if I give you a pen and I just draw if I just draw a continuous curve, what do I mean? It means that in principle, I can draw that curve with one pen stroke without lifting my hand from the paper. Okay? So you see that the previous function f was actually continuous because I was able to draw it with one pen stroke. But here, this function is not continuous because I can draw up to here with one pen stroke, but I have to lift my pen and put it back again after the point, yes? So this, I'm losing the notion of continuity. So that's extremely important. This was the reason that probably mathematicians were interested in defining a limit. They want to understand how we can define discontinuity without having the graph. Yes, because if I draw the graph for you here and I ask you, do you think it is continuous? Everyone understands that this is not continuous. But if the function is so complicated, how can I know that the function is continuous or not? I calculate the limits of the function. I calculate the value of the function. If they are not equal, so it means something strange is happening there. So I am losing continuity. And that is very important, by the way. Continuity is actually an important concept in whole mathematics. So is that clear? Okay, now can you imagine a picture for a function so that the limits are not equal, because all the examples that I've provided for you so far, the limits are the same. Yes? So not complicated, no, graph. Yeah, because if I ask you what is this function, I don't know. I just drew a graph here. Can you visualize? This is important for your lesson. Most of the time, you have to be able to do it, to visualize it rather than speaking very strictly. Yes. Can you, for example, tell me how to draw a graph so that the left limit is a number, the right limit is a different number. So here, the limits are actually, yes? Jumps up. Yeah, exactly. Discontinuity is even more vivid, yes? So what we say is that, for example, a function like this, I have a graph, for example, comes here, and then I put a hollow here, circle, and then from here I jump upwards, and then I will go actually from here to there. Okay, I want you to understand. So let me try to see. If this point is A, if this length is L, and if this length is M, first of all, tell me if this is the graph of function capital F of x. So what do you think about f of a? Can you answer what is f of a? Yes? M. Yes? F of a is not L because this is hollow, this is filled, so f of a is M. So we agree about that. Okay, but let us talk about the limits. I want to talk about the limit of my function. X goes to a. I want to understand this. To understand this, I need to think about what happens for f of x when x approaches a from the left, and then what happens when x approaches to a from the right. So in order to answer this question mark, I have to answer two more question marks. Okay? So how should I answer this question mark? Intuitively. So for the first question mark here, I am supposed to get closer and closer to a from the left-hand side. So let me stand here if you don't mind. Yes? And then this is the value of my function when I am here. It's not very far away from a, but I can do better. I can get closer. This is the height of my function. This is the length that I am now when I am here. I get closer, So what happens? It is increasing here. Yes, I get closer, it's increasing. I get closer, it's increasing. I get closer, it's increasing. But be careful, you are not allowed to answer this question mark. You even don't bother about thinking about point A itself. You only think about points close to A. So what happens at A is irrelevant. For this question mark, it's irrelevant to this question mark. It is not interesting for us. So what we go here, so now I hope that you have the intuition. What is the answer to the question mark? Is there any answer for the first question mark? Yes, what's that? It's L. Yes? And now let us get close to A, but from numbers above. For example, let me stand here. And then the value of my function is so big. Okay? But then I get closer. The value of my function is shrinking. When I get closer, the value is still shrinking. When I get closer, closer. Okay, now intuitively what happens to these lengths? They are getting closer and closer to which value in this case? M. So the answer to the second question mark is M. So the left limit is L, the right limit is M. In this picture, they are not equal. So these two are not equal. So what do you say for this one? The left limit, by the way, these are important. The left limit exists and is equal to L. The right limit also exists and is equal to M. But the limit itself, you say it does not exist. Okay? So it does not exist. Yes? I want you to understand the book is probably talking a little bit about these concepts, but the main point in the book is how to calculate limits. When it comes to calculation, then that is just algebra. And whatever you learned about rational expressions becomes really important. Yes, please.
So if we see in the graph that is continuous or one point is missing,
Yes?
then do we still have to write the x approaches a minus and x approaches a plus, where we know that both of them will be the same?
Yes?
Do we still have to do that?
No, let me just try to describe. I want you to understand the concept, okay? It doesn't matter how you convince yourself. If you just look at it and understand that they are not equal, you just write that the limit does not exist. But I want you to understand the process. In that case, by just looking at that, if you have already improved your skills, you immediately realize that the limit exists because there's one point out. But it's important to know that the limit, when the limits are not continuous, okay, or if the limits are not equal, something happens to the graph. The graph breaks into into more than one piece, so we lose this continuity. So that's a very important rule. Yes. Okay, so is that clear for everyone, the concept of limit? But the calculation of limit, I will tell you, this becomes more or less algebra. If I give you different functions and I ask you to calculate the limits, we will have some theorems that we can use to calculate limits, just like algebra, like solving equations. You really don't. This is why there is a danger. If I don't talk about these concepts right now, then probably you will never ever learn it, because you can immediately calculate limits without even understanding what you are calculating. Okay? So this is the last lesson we talk about the concepts. Next time I will probably talk only how to calculate limits. Yes? Okay. I think that would be a good idea. By the way, the examples that I have made it's probably giving you the wrong impression that when I get close to A from the left, the values are increasing, and when I am getting close to A, the values are decreasing. But do you think this is the case? I will come back to you. Do you think is it the case always? Is it always the case that when I get close to A from left, the values are going up, and when I'm getting close to A from the right, the values are shrinking? No, because you can imagine the other way around. Yes, for example, you can imagine this situation. I might have this situation, yes? And then what happens if this is A? When I get closer to A from the left, the values are becoming smaller. And then when I'm getting close to a, the values are becoming, when I'm getting close to a from the right, the values are increasing. When I'm getting close to a from the left, values are decreasing. So that is all. This is always possible. In those examples that I just brought, coincidentally, I just gave the examples the same. But I want you to understand this is not necessary. Yes, now, Carmen?
Yeah, you said, like, sorry that you did mention that this lesson we're going to be talking about the concept.
Yes.
I know it's a bit irrelevant to talk about how you solve it, but you mentioned that it might seem a bit overwhelming at first, but when it comes to the actual calculating part, it's just rational expressions and algebraic. Could you demonstrate an example of how it is so?
Yeah, exactly. For example, if I just give you this limit of x squared, the function that I started with, if I ask you to calculate this limit, of course you need to write the limit x goes to 1. Then we just use the tricks and techniques we solve for this. But be careful, because then you factorize this, and then x minus 1. And then, am I allowed to simplify x minus 1 and x minus 1? In the previous lesson, the answer is yes, because this is a factor, and that's a factor, and factors can be simplified. But I just also warned you in that lesson that the reason you can only simplify things if, first of all, they are factors. Secondly, what happens? Secondly, they are not zero. Okay? But in the previous lesson, if I gave you this and I ask you simplify it, if you do this and write x plus 1, I will give you the full mark, because implicitly I mean simplify when they make sense. Okay? But now you understand this really makes sense, because this symbol means x is very close to 1, but it is emphasizing that x is not equal to 1. So that is implicit in that symbol. Because I told you that when I say x goes, I will write them down for you. When x goes to a from the left, it means x is very, this very is a little bit vague here, is very close to a. This is something that you need to understand from looking at this symbol, but more, you need to understand, and x is smaller than a. So this, I want you to write it down. So this is the meaning of this symbol. And when I write x goes to a and I put a plus sign on top, what does it mean? It means, again, x is very close to a, again, and what? X is greater than a. This is the meaning of this symbol. And when you say x goes to a, it means x is very, again, not very clear, very, I have to have a good idea what is the meaning of very here. X is very close to a. And what should I write? And more than that. Means x is not equal to a. That is the only thing we know. But we don't know if x is greater than a or smaller than a. We don't know. So this symbol is giving you a message. It means x is very close to a, but it is not clear on which side of a x is lying. But it is clear that x is not equal to a. Okay, so that is implicit in this symbol. And in this symbol, it means it is very close to a, but x is less than a. And this means x is very close to a, and x is greater, absolutely greater than a, absolutely smaller than a, and not equal to a. So this is why, as you asked Carmen, that if I ask you to calculate this limit, you really don't need to bother about the concepts that much. But I want you to understand, because I told you that you can calculate the limit without understanding what is the meaning of the limit. So if I ask you to calculate this limit, the first thing that you do, you just factorize it as if we are simplifying a rational expression. But then even you don't need to bother to explain it to me. You can simplify them. But I want you to understand, why can I simplify? Because this symbol is guaranteeing that x is not equal to 1. When x is not equal to 1, x minus 1 is guaranteed not to be 0. And if it is not to be 0, I am on the safe side. I can divide by non-zero numbers, both linear. Yes? That's the mean. Yeah.
What if instead of x minus 1, it was x minus 2, but and x is approaching 1? Then
No, so that you can answer that question yourself. So what is your intuition? You ask this question.
no, x approaches 1.
Okay, then that would be the same problem. Ah, you mean this is x minus 2?
Yeah.
Okay. So if this is x minus 2, can you tell me what is the answer to this? No, but when you say that x goes to 1, that's also a good question. When x goes to 1, it means it is very close to 1. Very, it means that closer than 2 even. Okay? So that's a good question, because 2 is also close to 1. But when I say x goes to 1, it means that closer than any number that you can imagine. Something like this, if you want to. Yes? So this means that when you see this symbol, it is emphasizing that x is very close to 1, but not equal to 1. If x is very close to 1, closer to 1 than any imaginable number, then we are on the safe side. X is not 2 either. Yes? That's possible. So that's what these are very good questions you're asking. Thank you. Okay, is that clear? Yes or no? Okay, let me just try to show you an exercise to. We are finished now, yes? Yeah, we are actually finished. So I will actually give you more exercises next time, and probably we'll also talk about the limit. But this will be included in the coming exam. So I skipped some pages. I will come back to it. The main concepts in chapter 1 are rational expressions, factorizations, and limits, because we need all the package when we go to the next chapter, which is derivatives. Yes? Thank you very much. Yes, just a moment.